All right, so today I want to talk about pressure a little bit. Basically, air pressure. So, what is pressure? Pressure is a force. So, basically, air pressure is the force of the air pushing on your body in all directions, all over. And that's caused by gravity pulling all the molecules of air down towards the surface of the earth. So air pressure is the weight of all the air up to space pushing down on you on all over your body. And it's about 16 pounds on every square inch of your body pushing in. If your body wasn't pushing out with an equal force of 16 pounds, you would be crushed. So if you ever go underwater and if you dive deep down, like, 10 feet below the water, you can feel your ears pop, or you can feel the pressure. The weight of all that water is added to the air on top of it, pushing on you and squishing you down. And that's why submarines can only go so deep. If they aren't built to withstand the pressure of the water, if they go too deep, it will start to crush the submarine from the outside in, because the inside, the structure in the air on the inside isn't keeping the pressure out from crushing it in. So if you're going along with the Google Slides, okay, the slide has a jar on it with two kind of straws that go into a sealed jar, and there's a balloon with one. How could you inflate the balloon? Well, obviously, if you blew in the tube that's connected to the balloon would inflate. Is there another way you could do that? You could stop the video and try to think about it. Okay, the other way would be is if you sucked air out of the other straw, that would reduce the air pressure inside that's the jar that's squeezing the balloon closed. If you suck that air out, that balloon would inflate to fill the air inside the jar, because air would go through the straw into the balloon and it would expand to fill up the space that's in there. So either way, it would work. I love doing that demonstration in class, but I don't have the equipment to show you it at this time. The next slide is just another picture of the jar. Is a peep, a little marshmallow peep. Um, I have a vacuum jar in school that when you put it in there, and I boiled water with it before. If you remember earlier in the year, I put very hot water in there. And when I sucked the air out of it, it started boiling without adding any heat to the water. And that was just due to the air pressure. And I'll talk about that again a little bit later. Um, a marshmallow peep, it's nice and fluffy because there's a lot of little air bubbles inside of it. So if we put it in a vacuum jar and we start sucking the air out of it around the outside of the peep that's pushing the peep down, like crushing the peep down, we remove that air from the jar. What's going to happen to the peep? The air that's in the inside of the peep in little bubbles is going to start pushing out, and the peeps would grow in size, and it grows really big inside the vacuum chamber. And then when I let the air back in, the peep gets crushed down to way smaller than it was. That's because as the bubbles are expanding and rising, they're ripping apart, and some of the air that's inside the peep is lost. So then when the air comes rushing back in and you have 16 pounds pushing on the outside again, you don't have 16 pounds pushing back, so it crushes it down smaller. Are some of the demonstrations, and it's hard to imagine if you're not there in person with them. The shaving cream is much the same way as the PEEP. There's a lot of fluffy air bubbles inside of it, and in the vacuum chamber, it really expands. Um, and then eventually, when I let the air back in, it gets squashed down to like almost like a nothing puddle of like water, like white water in the bottom of it. Really neat. So if we go on to the next slide, we talk about properties of air. Air has the following properties. Now you can follow along with the PowerPoint, stop the video, read the slides and things like that. I think this will accompany that really well. Um, Density is mass divided by volume. So we can talk about how much volume does the air take up and what's the weight of it. Because air does have weight. Air has mass. They're made of particles. So each of those particles has a little tiny bit of weight. So the more you have, the more it's going to weigh. People say, oh, air doesn't weigh anything. It does. That's another demonstration in school I would do is I would take an empty balloon, weigh it, and on a balance, and then I would blow it up with air and put it on there, and we would see that the mass goes up. Um, So that's one of those things. Another one we can't show you, but air pressure is based on the density. So as you pull the vacuum the air out, there's not as many molecules that are bumping into you. And that's what the pressure is. The more molecules that are pumping into it are squeezing you. And as you pull them out, the air pressure decreases. So does the density of the air would decrease the same way. So we go into the next slide. You can see two boxes that have like equal amounts of particles on both sides. Okay. They randomly bump into the walls. So the pressure would be the same on both sides of the box. Is the way we're looking at it. So when gas is say how many particles are present in the area, how fast are they moving type thing. So a hot gas would have more pressure than a warm gas if there were the same number of molecules, because the hot gas, the particles would be moving faster, banging into the sides of the container a lot more frequently than a cool gas, and that would increase the pressure. That's why when a hot air balloon, it rises, okay, that type of thing. It becomes less dense, and we'll talk about that stuff a little bit later. So density, of course, we put the density triangle in there, the math equation for it. Density equals mass divided by volume. The next slide, it's an air molecule model. You see two boxes, one with a lot of particles and one with a few. So you can see that the density of the one with the more particles in it, it's greater, because there's just more particles striking the sides of the world. The pressure is higher on it, so the density is greater. So that density and pressure, they're kind of go hand in hand. Okay, there's just more particles banging into the sides of the wall more frequently, which means they're pushing on the sides of the wall more often. Very cool. The next slide shows they're about equal number of particles, but the one area or volume is much bigger. So if it's much bigger, the particles bump into the walls a lot less frequently. The pressure is going to go down. Okay, so the density goes down. The air density on that side is lower. So you're going to have a lower air pressure. So air density and air pressure are kind of equivalent. They're the same kind of thing. The particles on the right side of the diagram, you would see that they would bump into the wall a whole lot more often, adding more pressure to it. So we talk about the next slide. It says pressure. Okay, pressure is the force on an area or surface. Okay, so the more pressure, the more weight is pushing down on it, or the particles are pushing evenly apart. So when we look at the diagram there, the boxes, the one box on the left has a lot more particles on it. Okay, so they have a lot more pressure or a lot more weight of particles pushing down on it to increase the pressure. So that's kind of what it is. And that's really the kind of like basis for everything here. Pressure, okay? When it's high pressure, there's going to be pushing really hard. And if there's a gas, it's always going to go from a high pressure to an area that has lower pressure. It's going to be squeezed into that area. That is one of the biggest principles in all of weather that we have to consider. Now, here's a cool problem for you. The next one is the slide with the bus on it. Air pressure. On the top of the table, the weight of the air all the way up to space is about 16 pounds per square inch. And we're talking about the school tables, the tables that two people sit at in school. Those science tables in school, you take the square, how many square inches the table is, and the weight of the air pushing down on it would be about the same as a school bus. Okay, the weight of a school bus pushing down on it. Now, if we put a school bus on it, it would crash. It would just break the desk apart. But the air isn't doing that. Okay, there's got to be a reason why. So think about that for a minute or two and see if you can come up with an idea, and then you can restart the video again. Just work your mind. Try to think, why isn't the desk breaking apart? And when I come back, I'll fill you in on why. All right, hopefully you paused the video and you went through this and tried to figure out what it was. you have all that pressure pushing down from the top that should crush the desktop down, but the air pressure just pushes from every angle. So you have the same amount of air pressure from underneath pushing up on it. So you have pushing up and pushing down. They balance and cancel each other out. It's the same. So all that force pushing down, let's call it 5,000 pounds of force pushing down. You have 5,000 pounds of force pushing up, and 5,000 minus 5,000 cancel out. So it's evenly applied, which is it's really cool. So actually, the school desks, the school table, science tables in school are basically supporting a school bus of air pushing down on top, but helping it is the weight of a school bus of air pushing up on it too from underneath. So it's not just the table itself holding it up. These are kind of hard to understand, especially if we're not in class talking about them, but that's kind of why I went through this video for it. So on the next slide is the explanation. Okay, it isn't crushed because you have the air pushing up just as much as the air pushing down, and they cancel each other out. Now the balloon in the jar is the next slide, and to explain that is as you blow air into the balloon, you're pushing air out of the jar. Okay, through the other tube, through tube A, you're pushing air out of the tube. If I put my finger on that, okay, if I put my finger on that and you tried to, and I didn't let the air escape the jar, and you tried to blow the balloon up, it wouldn't blow up much. It would be very hard to blow it up because there isn't any room to push those molecules of air out of the way to expand into. Similarly, if I block that tube A and you try to, if you blew up the balloon and then I blocked tube A and air couldn't get back in, that balloon would stay blown up. Even though you take your mouth off it and stop blowing into tube A, it won't deflate unless I can let air back in that will squeeze that air back out. It's like I said, it's kind of abstract. It's hard to understand as it is, but it's kind of just the way. I just wish we could I could do this demonstration in front of you to show you. Now measuring air pressure, there's a couple different ways to measure air pressure. A barometer is one of the things that we want to do. There's two types. There's an aneroid, which is basically just a spring, and the air on the outside of it like compresses it in, and as the air pressure decreases, the spring can expand more or not. And there'll be like a needle that'll move back and forth as to how much the air pressure is pushing. It's a very sensitive spring. The other one, the first ones to the right, is a mercury barometer. They do them with alcohol now too, but mercury is what they first started with. You have a dish that's filled with mercury, a very dense liquid, and it goes up into the column. Okay, now the higher the air pressure is, the more it pushes on the top of the dish of mercury there, which pushes more mercury up the column, and you can see that the air pressure is rising. And if the air pressure decreases, it's not pushing as hard on the dish. So not pushing as hard, some of the mercury will go down the tube and fill up the dish and push back up on the dish a little bit. It's a pretty simple piece of equipment, but and it's very effective in showing the air pressure. There are the two types of barometers that are used. The explanation is on the next slide about how the air pushing down on top of the mercury pushes it up the tube. So the more air pressure it is, the higher the pressure, the higher it's going to go up into the tube. Now it doesn't change a whole lot, the air pressure around you when the weather changes, but this is sensitive enough to really detect it. A lot of people that have an injury or a broken bone can feel it in their bones. They're like, I can feel an ache in my bone, it's gonna rain. That's because you become sensitive to pressures like that at different times. It's pretty neat. All right, and going on to the next two, the aneroid barometer, the airtight chamber, that's what I just explained to you. There's a couple different, there's a few different scales that people use for measuring. And when it says units of air pressure, um, they use inches of mercury or millimeters of mercury, which is millibars. They can use that. Another one that's used is a Pascal for pressure, is another unit of pressure, and an atmosphere is a unit of pressure. The normal air pressure at sea level on Earth, they call that 1 atmosphere. That would be normal human atmosphere conditions, and we can go on from there. Um, like a like Venus, the pressure on that, because it's almost all carbon dioxide atmosphere, is way more uh, pressure than you would have at Earth. At the same thing, it's multiple times what the pressure on Earth is. It's another reason why it would be very hard to terraform that or put a base on there for humans to live on. The next slide has a mountain on it and talks about air pressure and density. Now, if you're at sea level at the bottom of the mountain, you can see the density of air is much greater. There's just a longer column of air pushing down on you. There's a greater weight of air. As you climb the mountain and you go up to the top of the mountain, you're at a higher elevation. There isn't as much air pushing down on you for up the space down to you. So instead of 16 pounds per square inch at sea level, you may be at 15 pounds per square inch up there. And the air's thinner, it's a little harder to breathe. When I went to Hawaii, to Mauna Kea, to the top of that mountain to see the observatories up there, I was getting out of breath. The air is much thinner up there. The air pressure is much thinner. So because of that, different things are going to happen. Water will boil at a cooler temperature than normally it would, because there isn't as many molecules pushing down on it. That was a demonstration I showed earlier in the year when we were talking about phase change. So altitude, it affects it, and that's the slide with the books. Where is pressure greater or less? Okay, at the bottom of the mountain, air pressure is much greater than at the top of the mountain because there's less particles pushing down on you. There's not as much weighing that column of air up the space. From sea level weighs more than the column of air from the top of the mountain up to space. And that's how we judge it, by the air density, the air pressure. It's pretty much the same thing. Where the air pressure is great, the air density is great as well. Okay, and then the next one is just that. Next slide is just basically do it. The last slide on there, this is one that's really important. Yesterday, we went through and talked about, or 2 days ago, we talked about the composition of the atmosphere, that 78% of the atmosphere is nitrogen. Well, as you go higher up, it stays that same percentage. It's evenly mixed throughout. It's still 78% nitrogen when you're at the top of the mountain, and it's still 21% oxygen. There's just less of all air molecules to breathe, so there's less oxygen. Still 21%. The percentage is still the same, but the overall number of oxygen is less. So say there's 1,000,000 particles that you breathe in at sea level. Well, when you get up to the top of the mountain, it isn't 1,000,000, it's 800,000 particles. So you're like 20% less air particles you're breathing in every breath. So you're getting 20% less oxygen and 20% less nitrogen, which means you're just not breathing as much oxygen. That's why athletes that have to travel to Denver to play an away game are at a disadvantage, because the people that live in Denver and play the night before, that whole week in Denver, are accustomed to thinner air and breathing thinner air, and their bodies acclimated to that and can use that lower levels of oxygen to perform better. Well, the people coming in, their bodies aren't used to that, and it takes them a day or two to get adjusted to using those oxygen levels. So if they come in the night before a game and then they got to play the next day, they're at a disadvantage. And even when teams from Denver fly out to another place, they're going to have an advantage for a day or two, that they're used to utilizing oxygen better. So in a heavier oxygen environment, they're getting even more oxygen in. So really cool things. Science is amazing. and we talk about all this stuff. Hopefully this helps. This video is a bit longer, so this will count for 2 days of an assignment. So it's not just for today's assignment, it also counts for tomorrow's assignment as well. So you have 2 days to complete the assignment for this. You have today and tomorrow. Okay, it will go in for both. Thank you all, and I'll be seeing you later.